Hello children, in our last discussion we learnt about equipotential surface. There we got the relation between electric field and potential gradient. Now today we will discuss potential energy of a system of charges in presence of field or in absence of field one by one. So let us start our discussion. First, electrostatic potential energy, and we will discuss in absence of external field. And we know potential energy is the amount of work done to bring a charge q from infinity to that point. And if charge q is brought to a point where potential is v, then work done w equal to q into v, where v is the potential at that point. Now we will take up two charges system. Let in this coordinate charge q1 is at point a1 is brought from infinity. Since it is brought in absence of field, so no work is done to brought the charge q1. But now in this system charge q1 is present. So due to charge q1 there will be electrostatic field all around. Now another charge q2 which is at infinity brought at point B with position vector r2. So by vector we can say distance between AB is r2 vector r2 minus vector r1. So here work done to bring charge q2 at B will be, if we see the formula, work equal to q into v. At point B, charge is brought q2 and potential at B will be 1 by 4 pi epsilon naught q1 by r12. So potential energy will be 1 by 4 pi epsilon naught q1 q2 by r12. In a similar way, we can find the electrostatic potential energy for three charges system as be done in two charges system. First we can say the amount of work done to bring charge q1 from infinity is 0 because no external field is present. Now due to this q1 there will be field. So if q2 is brought and q3 is brought, then at point B and C there will be potential due to charge q1. So the total work done to assemble three charges will be 1 by 4 pi epsilon naught q1 q2 by r12 plus 1 by 4 pi epsilon naught q1 q3 by r13 and 1 by 4 pi epsilon naught q2 q3 by r23. Similarly, we can extend our discussion for n charges system, and we will get for n charges system is as here. So if we see this formula, u equal to 1 by 4 pi epsilon naught q1 q2 by r12. Here see q1 q2 12 r12. 1 3 1 3, 2 3 2 3. So as we can extend, we can find. So on the basis of this one, we can solve a question. Let the four charges, each of magnitude q, are assembled on the corner of a square of size A. Find the electrostatic potential energy in this. And if a q naught charge is brought at the center of that square, then how much extra work is done? Now we will take up potential energy in an external field. And we know in a field, at every point there's a potential. So first, potential energy of a single charge. Let here the charge q is brought in the electric field E where potential V, then work done will be Q into V. So for a single charge, potential energy will be Q into V. Now potential energy for two charges in an external field. Let here external field E. First the charge Q1 is brought at position vector R1 from origin. Then work done in bringing Q1 from infinity to R1 is Q1 V at R1. Now another charges Q2, which is also at infinity, is brought at a point whose position vector is R2. Then work done will be Q2 VR2. And due to Q1, also there will be a potential at Q2. So work done on Q2 against the field Q1 is Q1 Q2 by 4 pi epsilon naught R12. Hence, we can say the total work done in assembling two charges in presence of external field is W1 plus W2 plus W21, and that will be Q1 V at R1 plus Q2 V at R2 plus Q1 Q2 by 4 pi epsilon naught R12. Now we will discuss, though this part we have discussed, a dipole in uniform electric field. Let a dipole of length 2L is placed at angle theta in the electric field. So the plus Q charge will experience a force QE in the direction of field, while minus Q charge will experience the same amount of force in opposite direction. So net force on the dipole is zero, so no translational motion. Though the line of action of these two forces are not same, so they constitute a couple, and the dipole will experience a torque due to this couple. And torque is given by electric force into perpendicular distance, and that will be force is QE and perpendicular distance is 2L sine theta, that is PE sine theta. Remember what is P? Dipole moment, that is Q into 2A. In vector form we can write P cross E. So here we see the direction P E at angle theta then the torque is into the plane of paper. Now if theta equal to 0, then torque will be 0, theta 90, torque maximum, that is PE, and if 180, again 0. Now we will discuss what is the electrostatic potential energy of an electric dipole in uniform electric field. Here see the configuration. Initially the dipole is at angle theta 1 in the external field. Now it is displaced by an angle d theta by the external force, and this position, the angle between now E and the dipole moment is theta 2. So if we remember the rotational mechanics, dw will be tau d theta and tau equal to p sine theta. So the total work done is integration theta 1 to theta 2 p sine theta, and its value will be pe cos theta 1 minus cos theta 2. Now the minimum potential energy will be if the dipole is at angle 90 degree with electric field. So if we take initial, that is theta 1 is 90 and theta 2 is theta, then potential energy U equal to minus P cos theta, that is P dot E. Now if theta equal to 0, then potential energy will be minus P. So it is the minimum potential energy. It is a stable equilibrium. If theta 90, then potential energy 0. And if theta equal to 180 degree, then potential energy is maximum, that is unstable equilibrium. That's for today. Thank you.